Hey dude, have you seen those old houses, ancient houses with curved doors and windows? They just so look like elegant and so classy at the same time. Ancient houses. I actually have seen them once in, I guess, pictures, Facebook, Pinterest, or somewhere else. But those houses are very ancient. They have this ancient vibe. They have this elegant and stylish look at the same time. Now, what I really like about those houses is that they have this specific history. That's what makes them really special, no? You're so right, dude. You're 100% correct. But here's the thing. Our client wants a house that has a similar design to ancient houses, and specifically the curved doors, with those curvature doors. However, here's our problem. Our problem is we must make the measurements as accurate as it can be in line with our client's demands while maintaining its elegant and classy look. That's quite a problem, bro. Why don't we use some sort of shape? It must not be square because it's too overrated and it's so overused nowadays. Why don't we use ellipse? Yeah, right, ellipse. Why don't we use that elliptical type of door with an ancient design? Now, Ellipse offers us a huge amount of design, huge quantitative amount of design, such as making ancient curves like that and so on and so forth. Now, this design does not only balances the overall ancient look and elegant design, but also helps us in computing the height and width of that door by using the parts of the ellipse. That's why we can actually use the concept of ellipse in building our elliptical door. The elliptical door is a very good example of structure that we can use in building the door of our client in line with his or her demand. You're so right, dude, about that. You have a point, actually. Because if we use its center, its vertices, its foci and axis, we can create a door that will look as ancient as possible, as elegant as possible, and as classy as possible while maintaining its accuracy and in line with our client's demand. You're so smart there, bro. You're right. That's why we're going to use math, specifically the concept or topic from pre-calculus, which is ellipse, in building our client's house and making his dream house come to life. That's why we're going to show them how we actually use the concept of ellipse in our door design. That's why we're introducing to you Sir Gab.
Hi guys, welcome to Pre-Cal 11. And today, we're going to tackle a very exciting topic in Pre-Calculus 11th grade STEM, which is ellipse. Now, in this video, we're not just going to discuss what are ellipse, what are the parts of ellipse, how to solve an ellipse, but also how to solve a real-life problem with ellipse. Now, let's tackle this topic with Sir Gab. Now, let's first start. What is an ellipse? An ellipse is a special type of oval-shaped curve that you often see in things like racetracks, planet orbits, or architectural designs. One more example of this is the Kabyang Tunnel for architectural designs. That is one example of ellipse. So in math, an ellipse is the set of all points where the sum of the distances from two fixed points are called foci, and they always stay the same. This can also be defined as the locus of points, whose distances from the focus is proportional to the horizontal distance from the directrix. And also, the ratio of the ellipse is called the eccentricity. Now, the eccentricity must always be less than 1, because if it is not, that is not an ellipse. So this is one example of ellipse. This is the planet's orbits, and this one is the parts of an ellipse. For the parts of an ellipse, we have the major axis, which is the longest line or longest chord in the ellipse. Next is the minor axis, which is the shortest curve or chord and the ellipse, and it's perpendicular to the major axis. Next is the center, which is the center point of an ellipse. The next one is the vertices, which are the 2 points of intersection of ellipse and the major axis. So the next one is the foci, the 2 foci. These are the 2 points, the F1 and F2, whose distances from the single point on the ellipse is constant. This is also denoted as C, because in ellipse we have to solve for A, B, and C, which are the values that is going to help us in solving the ellipse. So that is all for the part of an ellipse. I also wanted to add the directrix or the directrices, because there are 2 directrix and the 4 endpoints. Now moving on to the parts of an ellipse. As I said earlier, we have the major axis, and major axis is the longest diameter given in the equation. Next one is the center. This is the midpoint of major and minor axis. The vertices, this is the endpoint of major axis. Now the vertices is for the major axis only. The co-vertices, on the other hand, is for the minor axis. This is the endpoints of minor axis. Now for the foci, these are the 2 fixed points where the endpoints, the 4 endpoints, are along with it. Now the endpoints, it's the points that the minor axis and major axis connects. Directrices, this is a fixed straight line on the opposite side of the ellipse. Length of latus rectum, this is the perpendicular to the major axis and connects 2 points on the ellipse. Now length of latus rectum is also known as the LLR. Now this LLR is the length of the distance between the 2 endpoints, or when we divide that by 2, the distance is between the foci and the first endpoint. We will tackle on that later. Next is the length of major axis. This is the longest diameter in the ellipse. We can get the major axis by multiplying the value of A, which is for the major axis, by 2. And the last one is the minor axis. Minor axis is the shortest line that passes through the center of the ellipse and perpendicular to the major axis. Now, the length of minor axis is denoted as B, and we can get the minor axis by multiplying it by 2. Alright, moving on to our problem. For our problem, here's the situation. I am a specialized structural engineer or civil engineering. I am a civil engineering that is specialized in structural. Now a client approached me and requested for a house plan that is stable, stylish, casually small, and ancient elegant type. So in short, he wants a very modern-like structure of house where it embodies ancient elegant type. He requested that the main attraction of the house must be the door design, and can fit more than 2 people coming in at the same time. So maybe my client wants to have a very wide door for the people he's always inviting, because my client is a famous one. It's like if we compare him to an artist, he's like he is like Jericho. He's very famous. So again, he requested that the main attraction of the house must be the door design. Now I thought of this. An ancient elegant type of structure requires a bit of unique shaping, and it must house for about 2 or more people. Now upon discussing this idea with myself, I came up with an idea. I introduced to him the design that has never been done before in the history of modern ancient house designs. So this is the combination of modern and ancient house designs. And that is the elliptical type of door that fits the ancient, elegant, and modern look. The twist is, it's not just an elliptical door. It's calculated big enough that it can house for more than 2 people entering at the same time. Now, when I finished calculating this door, I was a bit surprised because my calculation is bigger than I thought, and my client was very much felt the bliss of having that kind of big door. Okay, next, we have to have our estimation for the door. So considering that the average height of a person is about 5.7 feet according to the World Health Organization, and 1.5 feet for the width. With this information, we can testify or justify that the door can house for about 3 people entering at the same time while maintaining the balanced height, which is 5.7 feet with an additional space for the head. In solving for the ellipse, our standard form is x squared over a squared plus y squared over b squared equals to 1. But then again, our door, which is an elliptical door, must be in a vertical form which is wide enough that can house for more than 2 people. That's why we're going to use this standard form, which is x squared over b squared plus y squared over a squared equals to 1. I've chosen that our axis would be y for the reason that I wanted to have a design that is tall enough with an average width for the door, which is our client request. So for the estimated height of the door that has a spacing for the head is about 8.5 feet. Now, if we input that to our calculator, so 8.5 minus 5.7, that would give us 2.8 feet of allowance vertically. For our estimated width of the door, we have 7.5 feet. Now, for 7.5 feet, this can house for about, when we input that to our calculator, 7.5 divided by 1.5, that would give us 5. So it can house for about 5 people entering at the same time. Now, again, as I said earlier, I'm a bit surprised with my calculation because my calculation was a bit underestimated because the calculation resulted in a much higher quantity of person entering at the same time. Now, let's calculate. Okay, so for our given information, we have these two. So we have the height and width, which has the allowance, which has the indicated allowance. For the height, we have 8.5 feet, and for the width, we have 7.5 feet. For the height, this would serve as our y-axis, and for the width, this would serve as our x-axis. Now, in solving for an ellipse, we have to first identify A, B, and C. Now, with this given information, we can now identify our A and B, which is 8.5 and 7.5. Now, with this information, we cannot just identify C by subtracting 8.5 by 7.5 because that process is for A squared, B squared, and C squared only, which is the Pythagorean theorem. Okay, in order for us to get the A squared, we just have to square the 8.5, and when we input that to our calculator, that would give us 72.85. Same goes with 7.5. With 7.5, when we square that, that would give us 56.25. Now, with this given information, we can now calculate for c squared before calculating for c. Now, using the Pythagorean's theorem, let's just equate c squared to a squared plus b squared minus b squared. C squared is equals to a squared minus b squared. Now, with that, we can say that 72 plus 85, 72.85 plus 56.25 minus. With this given information, we can now say that 72.85 minus 56.25 is equals to 16.6. Now, in order for us to get the value of c, we can just get the square root of 16.6, which is equivalent to decimal of 4.07. Now that we have completed the information that we are going to be needing in our computation for the ellipse, we can now identify our standard form, which is x squared over 56.25 plus y squared over 72.85. Again, our a squared would be in the y-intercept, and x squared and b would be in the x-intercept. Now, these are the parts that we must calculate in order for us to identify the exact ratio of the door. We have the major axis, the center, the vertices, the co-vertices, the foci, the endpoints, the directrices, the eccentricity, the length of major angle, the length of minor angle, and the length of latera recta. Let's start with the major axis. Now, as you can see, for our major axis, y-intercept has the highest value of 72.85. Therefore, our major axis, based on our standard form given, would be y-axis, in the y-axis. For our center, as you can see in the given, there is no value beside x and y. So, do you think, class, that we must input 1 or 0? Of course, if there is no value beside x and y, therefore our center is at 0, 0. Alright, for our vertices, we will need the value of a in our vertices. Since the vertex of our ellipse would be at y-intercept, for the reason that it has the highest value, our vertex 1 would be at 0.8.5 and vertex 2 would be at 0 and negative 8.5. We just used the value of a without using the formula, because in ellipse, you'll just be needing the use of formula when you are encountering h and k. So when you're encountering h and k, you must use the formula in order for you to have an accurate answer. For our co-vertices on the other side, let's just use b, but this time on the x-axis. This is for the horizontal axis of the ellipse. Therefore, our b1 is at 7.5 and 0, and b2 is at 7.5 and 0. Now, for our foci, let's just use the value of c, which is 4.07, but this time, again, in the y-axis. Because according to our pre-cal teacher, in order for us to have an easier time or easier manner of answering ellipse, let's just imagine that if our major axis is at y-axis, let's input a as y, B as x, and C as y. And if it's on x-axis, our A would be at x-axis, B at y-axis, and C at x-axis. So the pattern will go like x, y, x, and y, x, y. So again, for our foci, it would be 0 from the center again, and 4.07. And for our foci number 2, that is 0 and negative 4.07. Now for our endpoints, this is where it's going to get a little bit tricky. We have to use a formula. We always have to use a formula for the endpoints. Now for the endpoints, we have 4 endpoints for the ellipse. Take note of this class. For the first endpoint, we have to use the formula h plus b squared over a and k plus c. So I'll show you the endpoints first before computing it. So for our endpoints 1, we have 6.6 and 4.07. Now let's see if that is correct. Use your calculator with me. So the formula for solving for the first coordinate would be h plus b squared over a. So that is what our h is 0 plus b squared over a. So let's just compute b squared over a first. Our b squared is 56.25 divided by 8.5. That would give us 6.6 or approximately 6.61. So 6.6 is our first coordinate for x-axis. For our y-axis, let's just add k plus c. So our k is 0 plus our c, the value of c, is 4.7. Therefore, 0 plus 4.7 is 4.7. So our endpoints 1 is correct. For our endpoints 2, our formula again is h plus b squared over a, but this time, the next coordinate for y-axis is k minus c. So let's check. So for our endpoints 2, we have to use the formula of h minus b squared over a and k plus c. So for the endpoints 1, we have used h plus b squared over a, but this time we're going to use h plus b squared over a. And that would give us, again, input that in your calculator. Our h is 0 and b squared over a is 6.6. So that would give us 0 minus 6.6 is negative 6.6. And k plus c is again 4.07. So our endpoints 2 is correct. For our endpoints 3, we just have to use again h plus b squared over a, but this time we have to minus k subtracted to c. So our third coordinate for our x-axis would be 6.6 again, and for our y-axis that would be negative 4.07, because 0 minus 4.07 would be negative 4.07. For our endpoints 4, we have to use h minus b squared over a and k minus c. So let's input that in our calculator. H, which is 0, minus b squared over a, which is 6.6, that would give us 6.6. And for our y-intercept, which is k minus c, our k is again 0 minus c, which is 4.07, that would give us negative 4.07. So take note of this, class. I will enumerate again the formulas for E1, E2, E3, and E4. For E1, it is H plus B squared over A and K plus C. For E2, H minus B squared over A and K plus C. For E3, H plus B squared over A and K minus C. And for E4, H minus B squared over A and K minus C. So I hope you've written down that information for the endpoints, or that formula for the endpoints, because that would really help you in solving for the endpoints without guessing the coordinates based on the graphing paper. For our directrices, let's just divide A squared by C. That is the formula, okay, class? The formula for directrices in getting the directrices is A squared divided by C. So 72.85 divided by 4.07, that would give us 17.89. So in writing this one, since our major axis is at y-axis, we have to put the directrices value in an equation for the y-axis, because again the directrices is the fixed line in the major axis. It is the point of intersection of the fixed line. Therefore, our directrices is located at positive, negative, 17.9, and 0. I just forgot to... 0 and 17.9. That is 0 and 17.9. That is the coordinates for the y-axis. But I've just written positive and negative 17.9 here for us to have a shortcut. But for the coordinates, that would be 0 and positive 17.9 and 0 and negative 17.9. Okay, class, I hope that you're still following with me, because we have to still solve for the 4 parts of the ellipse. For the eccentricity, this is just basic. We just have to use the formula C over A. Our C is 4.07. Input that in our calculator for basic calculation. 4.07 divided by 8.5. That would give us 0.47. Now again, for the ellipse, the eccentricity for the ellipse must be less than 1 for you to consider it as an ellipse. Since the eccentricity is 0.47, that is confirmed an ellipse. For the length of major axis, let's just multiply A by 2. For the formula for the major axis, that is 2A, or A times 2. So 2 times 8.5, that would give us 17. Now for the length, it is measured, or the units is measured in the units. So the length of major angle, or the major axis, is 17 units. For our minor angle, let's just multiply B by 2. So multiplying B by 2, 7.5 times 2, that would give us 15 units. So again, the formula for major angle is 2A, or 2 times A. Length of minor angle is 2B, which is 2 times B. And for our lateral recta, let's just multiply B squared over A times 2. So our B squared, let's do this step by step again. B squared, our B squared is 56.25 divided by 8.5. That is again 6.6. Now, in order for us again to solve for the length of lateral recta, we have to double the value of the b squared over a, or the latus rectum. So our latus rectum is 6.6. Let's just double that. Let's times that by 2. That would give us 13.2 units, or approximately 13.23 units. Now, these are the values that we are going to use to build the door. So these are just the basic mathematical values that we are going to use to build the door. Easy, right? Problem solved. Okay, now that we have these values, we can now start by graphing this one into a graphing paper first before conceptualizing or constructing the design. So let us first point our center, which is at 0, 0. So as you can see here, class, there's a point at 0, 0, which is our center. For our vertices, we have 0.8.5 and -8.5. So that would be located at the upper portion of the y-axis and the lower portion of the y-axis, and you can see here visually in the screen. For our co-vertices, that would be located at 7.5 and 0 and -7.5 and 0. Look, that is located at the right portion of the x-axis and left portion of the x-axis. For our foci, that is located at the y-axis again, that would be 0 and 4.07 and 0 and -4.07. So we're getting near, class. Let us now locate our endpoints. So our first endpoint is at 6.6 and 4.07. That would be located at the first quadrant of our plane. For the next one is -6.6 and 4.07. That would be located at the second quadrant of our plane. And for our endpoints, 3, that is 6.6 and -4.07. That would be located at the fourth quadrant of our plane. And for the last one, which is E4, -6.6 and -4.07, that would be located at the third quadrant of our plane. So we're almost done. Let's just locate our y-axis, let's just locate our directrices, which is at 17.9. So as you can see here, there is a point at 17.9. This is where the line cross. Okay, class? Okay, we can now plot the lines for the ellipse. So it would look like this. So as you can see, the graphing paper is very much corrupted, because in the graph you can see that it's like an x-axis major angle. But keep this in mind that I just used the Google graphing paper, and this is the graphing paper that has the most number that I can see or that I can find. It's still in the y-axis, and I will still fix this by expanding. So our center is correct, our vertices is correct, co-vertices is located right, our foci too, endpoints are located in the right place also, and the directrices is located at the right place also. So we're very much good to go. Now this is the very much exciting part that I was telling you earlier. I told you that the ellipse can just house for about 5 people, right? But when I estimated it, it can house for 7 people. Can you imagine that? I've underestimated my calculation. So with that, I proposed this to my client, and he was very much happy with my proposal of the design and the calculation for the elliptical door that is aligned with a modern, stylish, lavish, and elegant with an ancient spice of look. So for the final design, I've designed this in Ibis paint, and this is what the design that is going to look like. This design does not only implicates the elegant look but also embodies the ancient look, because most of the door like this does not have the ancient look for the reason that they have modernized everything. Actually, I would just have added some color palette, which is some brownish, orange, dark blue. I would just have added that palette to add more depth and ancient look. But for now, this would be the design, a customized design for the elliptical door for my client. Now again, problem solve. This is the problem that I've been wanting to solve for a very long time now. So in conclusion, that is our finished, stylish, ancient looking door, all made possible with the concept of an ellipse. It's amazing how a simple mathematical shape can turn into something artistic and elegant. The ellipse helps us create the smooth, balanced curve that gives the door its unique and antique vibe. This project really shows that math isn't just about numbers. It's all about creativity. It's about your mind. It's about going beyond on what it is set, or going beyond on what it is expected. Geometry can bring structure and beauty together, especially in design and architecture. So, class, what do you think? What do you think of the design and computation? Do you agree or do you cohere with the design and computation? Let me know down in the comments below. Would you also try using the math concepts like that I did in your ellipse own projects? Let me know, okay? Thank you for watching, and always remember, math isn't just something we solve. It is something we see in the world around us. It is something that is useful. It is something that provides us utility and maximizing our creativity with it. Thank you so much for listening and helping me solve the problem for my client, which is the elliptical door. Now, this is Pre-Cal 11. I am Sir Gab, and I am so much grateful for having you. Till next time, class. Bye-bye.